I'm very excited to talk about this pipeline pilot protocol and how I believe it can really transform our industry, or at least begin to transform our industry, because for those of you that do ligand design, you're well aware that what often happens is you have a model or a series of models that can help you, for example, optimize one particular property, let's say ligand binding. We've heard today from Brad Pierce about techniques that can be used to predict ligand binding. But all of us, of course, in the industry, pharmaceutical industry, well understand that that's just one property of many that need to be simultaneously optimized into what we call a drug, and that's what we're trying to bring to market. So I want to begin with a scenario, and this is really to illustrate proof of concept. Here is a compound. This is a cholecystokinin antagonist that was developed by Merck in the late 1990s. This compound has activity in the rat. It has an IC50 of 300 nanomolar, but it has some problems associated with it. In particular, the predicted brain-blood barrier of this compound is not very good, so it's negative 0.58. And remember, that's the log 10 of the ratio of the concentration of the compound in the brain divided by that in plasma. So you'd like that number to be positive. And in particular, also, of course, the solubility of many compounds are often not desirable, and this is no exception. The predicted solubility of this particular compound is almost -6. Now remember that what that really means is the solubility would be 1 × 10 to the -6 moles per liter. So we'd certainly like compounds that are more soluble than that. So therefore, if we were to take a compound like this that might be a lead in some optimization program, we'd like to try to simultaneously optimize a number of properties all at once and do it as quickly as possible. So we want to maintain or improve the biological activity. We'd like to maintain or decrease molecular weight. We'd like to maintain A log P within some reasonable range. We don't want extremely hydrophobic molecules. And we certainly want to improve this blood-brain barrier partitioning. We'd also like to try and improve solubility. Now, here's where this becomes difficult. Let's take, for example, the blood-brain barrier partitioning and solubility. If you look at two equations from the literature, this is equation 6 is an equation predicting blood-brain barrier partitioning coming from Clark. This equation for solubility comes from the work of Samuel Kalski at the University of Arizona. And if you notice, what's happening here is that the BBB partitioning would increase if we could somehow decrease the polar surface area of a molecule, but we want to increase the log P. But that works to our detriment in terms of trying to increase solubility. So if you believe this equation, for molecules that would have approximately the same melting point, as we would increase log P, that would decrease solubility. So therefore, the issue is, how could we possibly simultaneously optimize properties that would, at first glance, seem to somehow conflict with one another? Is it even possible? The other aspect, as I mentioned, is that we really need a tool that does what I call direct route drug design. And again, this is just a cartoon, but I think it captures much of the truth about what happens in our industry. Namely, HTS campaigns will easily find lead molecules, and then through some sort of screening paradigm, will optimize one particular property. For example, in this case, we might march along this axis trying to optimize the blood-brain barrier partitioning of a molecule. And here I'm showing 3 steps, but really that's a cartoon, okay? Many times it can take 10 steps and 100 steps, 500 molecules to actually get molecules that have improved blood-brain barrier partitioning. And then once we reach a compound where it's been partly optimized for that particular property, then we move along another dimension where we're trying to optimize, for example, against solubility. So what happens is, instead of going directly from our home to the grocery store by the direct route, we go this kind of circuitous route, and it takes too many steps. So again, we need to find a way to go directly from, for example, a high-throughput screening lead to a drug. Now, Vilfredo Pareto was an Italian economist and also philosopher in the late 1800s and the 1900s, and early in this century, past century, I'm sorry. And one of the concepts that he came up with was this idea of what's termed a Pareto front. And let me just go over this concept quickly. If I mumble or I don't say something clearly, just try and read along in my slide. This was taken off the Wikipedia. So let's assume that you have a set of points in some sort of space that you're trying to optimize two properties. And clearly, there are various values of those particular properties, F1 and F2, for those particular points. Now, let's just suppose in this particular case that we're looking for points where the F1 value and the F2 value are both as small as possible. So that would be points heading down towards the origin. Now, let's look at 3 points in particular, A, B, and C. Point C is clearly not an optimal point because, for example, although the F2 value is minimal, we can find another point, A, that has a smaller value of F2. And likewise would be true for any points located in this region. But points along this curve that's sometimes called the Pareto front or the Pareto frontier represent a set of points where there have been trade-offs in those various properties, but it sort of represents the best set of points or the best set of compounds in the case we're really interested in that satisfy these particular properties. So this is the idea behind the Pareto optimization that I'm going to be talking about today. So we have, the idea originally came from Vilfredo Pareto, but it turns out that we have this gentleman, Dana Honeycutt, who likes Italian food. No, just kidding. I don't know that he knows that. But anyhow, Dana is a very bright fellow, and I encourage you to talk to him about some of your interests and so forth. But the good news is that the latest version of Pipeline Pilot, and this was, I believe, incorporated in version 7.0, came out in 7.0. There are 3 components that allow you to do these different Pareto optimizations. There's a Pareto combinatorial optimizer, a Pareto sort component, and a Pareto subset optimizer, which is what I've used, and I'll talk about that in just a few slides. Again, the idea here is that you have one or more compounds at iteration 0 that are, of course, not optimal, and you perform a set of transformations or changes on those molecules, generating a set of molecules here that have been optimized along that Pareto front. And in this case, we're trying to optimize both blood-brain barrier partitioning as well as solubility. We do another set of transformations that generates iteration 2, and so on, and we're trying to drive along that simultaneous vector in those 2 components. Now, one of the ways I had to get this to work within Pipeline Pilot is as follows. I decided to create an objective function that is simply a weighted linear combination of a term involving the calculated blood-brain barrier partitioning and the weight involving solubility. Now, this function has a couple of interesting and useful properties. Number one, because it's been weighted appropriately, what I'm trying to do is balance the components of the blood-brain barrier with the solubility so that they more or less have an equal weight. And also, because of the scale factor in the offsets, this term in the function would have a maximum value of approximately 1. This term in the function will have a maximum value of approximately 1 as well. Therefore, since 1 plus 1 is 2, at least it used to be, it means that when we see the value of the objective function approach 2, it means that we're finding compounds that are reaching this theoretical maximum of the objective function. So it's a convenient way of keeping track of how good we're doing. Now, because we have to create new chemical matter, we have to somehow generate new molecules. One of the ways that that can be done is using software that was created by my colleague Kent Stewart and his associates back at Abbott. What Kent did was, he comes from a medicinal chemistry background, but he's been surveying the medicinal chemistry literature over the years, and what he has come up with are a set of SMERCS transformations that have been found statistically to quickly enable conversion of molecules from hits into molecules of higher quality. So what I've done is basically stolen his set of SMERCs, and there were 259 in his original work. He's since supplemented that list, and I converted those to MDL reaction files, and I will show you a component in Pipeline Pilot that can easily read those reaction transformations, and that's the engine that will drive the creation of new matter in the optimization process. Another tool that's necessary in this optimization, because again, you heard earlier Brad Pierce talking about doing structure-based ligand design, where you're talking about docking and scoring molecules in the crystal structure. In this case, the cholecystokinin antagonist is a ligand that does not have a crystal structure, so we have to have some way to judge the activity of that molecule, and that's done through similarity and belief theory. I won't go through all the details of that. That was published in some work that Steve Muchmore and my colleagues, we talked about this last year. But the idea is quite simple. Namely, what we've done is we've looked at a number of cytigic and other fingerprints. And here, for example, is the Tanimoto similarity in green. These green filled circles are the ECFP_6 fingerprints. Similarity versus the percent active found through database retrieval. And so if the Tanimoto similarity, using, again, the ECFP_6 fingerprints, is 0.4 or higher, this means that we have approximately a 24% probability that the compound will be equally active to a reference compound. And remember, I told you on the second slide that original cholecystokinin antagonist was active in the rats. So we know already that the reference compound is active. One other tool that's used is basically, as we're creating new chemical matter, we have to have a number of filters that get rid of garbage, because these de novo programs do generate things that we're not interested in. So again, approximately 2 years ago, myself and several colleagues, we published a paper in which we developed a Bayesian classifier, again using Pipeline Pilot tools, that looks for the probability that a compound will have a level of unacceptable reactivity with what's called the La protein, which is a protein that has a large number of thiol groups. So this is a marker for undesirable ligand reactivity, and it's used to help filter out molecules during the optimization. Okay, now, since this is a users group meeting, I want to just sort of very quickly give you a sense of how this protocol, what's really in the guts of this protocol, what's it really doing. So the first step is, because we're going to be optimizing, doing multiple runs, and it's never quite obvious how to set particular parameters to get the best results, what I found convenient to do is to use a text file that allows me to set a number of global parameters and read those in. And in this case, I'm reading about 50 parameters. The current version of the program is now reading about 200 parameters, so it's expanded quite a bit since I first created this protocol. But nevertheless, this is a very convenient way to read in a text file and set simultaneously a large number of global parameters that will be in effect throughout the entire protocol. In the second and third pipelines, what we're going to do is we're going to read in a reference molecule, because, remember, we have to compute that Tanimoto similarity to make sure we're not creating molecules that go too far astray from the reference molecule. So we read in that reference, we read in the parent molecule, go through a number of steps here, we compute the objective function for that particular starting molecule, and here is the objective function, which again is this linear combination of the predicted blood-brain barrier partitioning and the solubility. And we write that information out to an SD file and a text file, and then we compute some more statistics, write that out to a CSV file. Now, what's interesting here is that, it may sound trivial, but this capability is actually quite important, is that rather than rewriting this text file at every step, I'm actually appending to it, and that allows me then to monitor the progress of the optimization at each step, because I can simply read in that text file into some statistics program and make a plot, very simple plot, of the iteration number versus the objective function, and that tells me how well the optimization is proceeding. Here's another step in the protocol. In this case, we're using this generate empty data component to drive a run-to-completion subprotocol, any number of steps. So here we have a global parameter, maximum number of iterations. I typically do runs using anywhere from 20 to 50 iterations, but it's easy to set that as a global parameter in that text file I mentioned. And again, that drives this run-to-completion subprotocol. Now let's go actually open this up and see what's inside here, and that's where it gets very interesting. There's a lot of detail here, so I'm not going to go over every single component, but again, just to kind of highlight a few things. So again, we read in generations of molecules inside the run-to-completion subprotocol using this SD reader. We come down here. That's written to a cache. Here we also read in those compounds again. Those large subsets that are created are fed into the Pareto subset optimizer. Now here what's interesting is that I'm actually calling a separate component, which is this custom objective function. So I'm calling a completely different subroutine that contains this formula, and that's actually creating the objective function itself. Finally, the last two components inside the run-to-completion subprotocol are here. Again, I read in that reference molecule, read in molecules from the Pareto optimized subsets. It's this little component that's reading those 259 transformations that I mentioned. And actually, I forgot to point out that in addition to my colleagues' 259 transformations, I've added, I believe I'm up to about 300 additional transformations. So we're talking about every single molecule that comes into this component is examined, and if it matches the transformation query, it can create up to 500 or 600 new molecules. So again, those new molecules come in here, they pass through a number of filters, come back up here, and the similarity of those new molecules is compared to the reference molecule. And if it passes, then it's written out to these SD files and so forth. All right. So here, this slide summarizes then both the set of filters as well as the Pareto properties that are being optimized. I'm not going to go through all this detail, but essentially it's necessary to use not only filters, but again, control the optimization through these Pareto-weighted components here. In this case, the blood-brain barrier partitioning and the solubility. This is the objective function that I've already mentioned. Here are the results. So this slide, this plot on the right-hand side shows you the iteration number. So this is as the optimization is progressing versus the objective function. So you start out with molecules that are not optimized. In this case, that was the initial single input molecule, and the objective function builds up, and eventually it levels off. Now what you see, if you look at the information along in the BBB dimension and the solubility dimension, here these numbers are showing you the iteration numbers. So here's iteration 0 and 1, iteration 2, iteration 3, 4, 5, and 6, and so on. But what you see is that there is a clear progression where we're improving both the blood-brain barrier and the solubility. So it's going along this vector, and that's exactly what we want. Now what's also interesting is that once we get to the 6th iteration, the optimizer kind of takes a, I don't know why, but it somehow takes a sidestep in that the blood-brain barrier, predicted blood-brain barrier of the molecules doesn't seem to improve much, but we see an improvement in the solubility. And so you see further iterations going kind of up and back this way. Now let's look at, make a quick comparison here of the input molecule that we started with versus iteration 6. Notice that the blood-brain barrier component has improved, and the solubility has also improved, and that's exactly what we want. Another question then becomes, well, again, back to the drug design problem, many times it isn't just 2 problems, there might be 3 problems, or 4 problems, or 5 problems. And again, we need to find a way to create drugs that can simultaneously improve all of these properties all at once. So can we even do that? So here's a case where I've extended the optimization to another property. So we still are trying to improve the blood-brain barrier partitioning, improve the solubility, but this compound also has a predicted CYP2D6 probability of 0.50. Now what this means is that there's a 50% probability that this compound will be a CYP2D6 inhibitor. And you don't want that, because if you have compounds that are inhibitors of cytochromes, that can cause drug-drug interactions. So you want to reduce the probability that the compound would be a CYP inhibitor. Can we do that? Again, it's necessary to set up parameters controlling the filtering process, parameters for the Pareto optimization. In this case, I've simply added a parameter in this linear function now for the CYP2D6 probability. But notice something carefully here. The weight on this CYP2D6 probability is -1. It's negative because I want the probability to go down, not up. Since we're optimizing 3 properties, we have to look at this in a sort of a 3-dimensional space. But before we do that, let's just again look at the iteration number as a function, the iteration number versus the value of the objective function. Again, what you see, starting from our initial molecule, the objective function increases, and it tends to level off. But it's doing basically what I want it to do. I want it to improve the objective function. Now let's look at this in more detail in 3 dimensions. I tried to have a kind of a rotating cube, but I couldn't quite figure out how to do that. So bear with me. I'm going to try and guide your eyes through this slide. Along this axis is the value of the blood-brain barrier partitioning. So as we move in this direction, we're improving or increasing the BBB. Along this axis, going up, we're improving the solubility. And along this axis, we're improving or decreasing the probability that the compound would be a CYP2D6 inhibitor. So what we want to do, so think in your mind, we got 3 vectors. We want to make them all go in the right direction. So what that means is we want to start here, we want to go across, up, and back into that cube. And that's exactly what we're seeing. So here's, again, the initial molecule, iteration 0 and 1. We're going back, across, up. So step 3 to step 4 is an up step. And then we're going iterations here, 5 and 6, and we're also going up. So it's doing exactly what I want it to do. Again, in summary, if we look at the values of the input molecule versus iteration 6, the blood-brain barrier partitioning has improved, solubility has improved, and the probability that the compound would be a CYP2D6 inhibitor has decreased significantly. So it's doing simultaneous multi-property optimization, exactly what we want to do. Okay. One final scenario. So if we could do it with 2 properties, could we do it? We did it with 3 properties. What about 4 properties? This compound also has a predicted hepatotoxicity probability of 0.92. And this number means, again, that there is a significant probability that this compound, as it's drawn, would be a hepatotoxic substance. And you don't want that for a drug. So the question is, can we somehow modify this structure to get away from that probability and simultaneously optimize all these other properties? So it's necessary to create these global parameters, as I've done in the other optimizations. And again, I just added an additional term down here, the ADMET hepatotoxicity probability. And again, because I want the probability to decrease, the weight on this particular term is a negative value, negative 1.0, instead of a positive value. So you can simply construct this linear function in the Pareto optimization. This is our objective function. Here are the results. Now, because we're optimizing 4 properties at once, you can't see, I can't easily show you some visual of a 4-dimensional thingy, but we can sort of slice and dice this looking at 1 dimension at a time. So let's first look at the progress of the objective function as a function of iteration number. And again, we're seeing the behavior that we'd like to see, namely the value of the objective function is increasing as the iteration number increases, which means that we are simultaneously improving the values of all 4 of those properties. Now here is sort of looking at each property in detail. The blood-brain barrier value of these compounds is improving, so it's going up as a function of iteration number. The solubility is improving as a function of iteration number. Here is the CYP2D6 probability. Again, we want this to go down, and that's exactly what we're seeing as a function of iteration number. Also, the liver or the hepatotoxic probability is also decreasing significantly as a function of iteration number. So we are, in fact, simultaneously optimizing 4 properties starting from this initial molecule all at once. And again, this table summarizes the changes in all 4 of those properties. They're all going in exactly the right direction. So let me just summarize then. So this program, Pareto Ligand Designer, can effectively drive multiple objective ligand optimization in 2, 3, 4 dimensional property spaces. And you may ask, well, what about 5, 6, 7, and 8? I honestly don't know. I haven't tried it, but I'm optimistic that I tend to think it might work. The program clearly demonstrates proof of principle, although some of you may argue that some of those changes are very modest, and I would not disagree with you, but I think it does nevertheless demonstrate proof of principle. The set of molecular transformations, it's very easy to extend them, and I'm currently doing that. And it's also important to think about, well, it's one thing to have a molecular transformation where you go from, say, a benzene to a pyridine or from a pyridine to a benzene. That's not a real chemical transformation. But keep in mind that, for example, the folks at ChemAxon make available pipeline pilot components that do chemical transformations with real chemistry. So, for example, you'll have a reaction that does a Williamson ether synthesis, or Friedel-Crafts alkylation reaction, or for some sort of Clemmensen reduction or something like that. So it is possible to replace the molecular transformations that I've used, which are more of an alchemical sort of nature, with real chemical transformations that would be available in this component. And in fact, I'm already working on this, and I think it's going to work out just fine. I didn't have time to talk about this today, but again, Brad was talking earlier about doing free energy calculations where you have a core structure and you're essentially varying R groups about that core and trying to calculate the free energy binding of that particular set. Now, you can do something very parallel to that using this program. So, for example, in Pipeline Pilot, there is a component that's called a deprotect or a protect module. What you can do is you can, so given a molecule, like, for example, that cholecystokinin antagonist, you can create a subset of those atoms, so it would be your core, that can remain fixed. And what you can do is then look at the optimization or what substituents would be created, assuming that you allow the core to vary. And you can also do the inverse of that. In other words, you can select the R groups, you can protect the R groups, and run this program such that you're trying to understand if I want different cores, so I don't like my core. Maybe it's a benzofuran that has known toxicity or something like that. You want to get rid of that core, but it's necessary to maintain those R groups because you know from the SAR that they're important. So you can also run this program in the kind of an inverse mode where you try and get rid of the core. A couple of other items. It is very easy to incorporate additional filters. As I said, I've been working on this for a number of months now, and it's not very difficult to add, for example, SOAP protocols or SOAP calls to, for example, gold that already exists, to, for example, this program from Rengshao Wang that does protein ligand PKI predictions as well as shape matching, program ROCKS from the OpenEye folks, and working on some of that as we currently. And another very interesting concept is that this particular program might be used to examine what I call the likelihood of success. So you could imagine if you were a chemistry group leader and you had a group of chemists and you have to somehow, and say, for example, you have 3 or 4 chemotypes that are being explored in a chemistry program. What you as a chemistry group leader need to figure out is, how am I going to allocate? I've got 10 chemists. I don't have any more. And do I want an equal number of chemists working on each chemotype, or do I want somehow an unequal distribution? And how would you rationally decide how many chemists I want working on a particular chemotype? So what you could do here is very interesting. You could take, for example, your chemotypes or the cores representing those chemotypes, run them through this program, and ask the question, if I were to optimize around a particular core, and suppose I could do 20 rounds of optimization, what would be the relative values of those objective functions for those different chemotypes optimized through the same objective function? In other words, what chemotype is going to give me a higher probability of success? And I believe this is a tool that could very easily be used to do that. All right, I'd like to finish by thanking my colleagues in the structural biology group. These colleagues have been very helpful in our scientific computing group, maintaining the software and pointing out some various statistical issues. And I'd very much like to thank the support folks at Accelrys. I've said this before when I've talked at these user group meetings, but when you're dealing with very technical software, you need to have a highly skilled, helpful support group. I mean, it just is absolutely essential. And I'm just so thankful that Accelrys has it. In particular, I've had many, many helpful conversations with Keith. He's a very nice chap, very, very helpful, very bright. Dimitri has also been helpful in suggesting how to set up this looping algorithm that's very important for the optimization process. And I've already given some credit to Dana, who was really one of the, who was, in my opinion, the software developer for the Pareto components. And if he didn't create those components, I would not be here talking to you about this. So I'm very thankful for all these folks who contributed to the success of this protocol. And I thank you for your time.